Next we want to look at the 3 Cnf Sat. Okay, so this is a formula satisfiability, but a couple of things that we're adding to it. First of all, the formula has to be in conjunctive normal form, and then it's in 3 conjunctive normal form. So that means each clause has to have exactly 3 literals in it. Okay, so let's just kind of review a few pieces of terminology. So a literal is either a Boolean, in a Boolean formula is an occurrence of a variable or its negation. Okay, so that means like x, that's a literal, and then not x is also a literal. Okay, so either one of those would be considered a literal. And then a clause is going to be the or of one or more literals. Okay. And a Boolean formula is in conjunctive normal form if it's expressed as an and of clauses. So that and, that's a conjunction. The clauses are disjunctions. So your conjunctive normal form is a conjunction of disjunctions. All right. And then a Boolean formula is in 3 CNF if every clause contains exactly 3 distinct literals. And that's important. We have to have exactly 3, and they all have to be different. Okay. And so we would like to prove that 3 Cnf Sat is NP complete. Okay. And so in terms of the first step, so remember NP completeness proofs, the very first step is always to show that the language or the problem is in NP, that is verifiable in polynomial time. Okay. And really the argument is basically the same as it was for satisfiability. You just take the certificate, the assignments to the values, you replace all of the literals with their values, and then just evaluate all of the logic expressions for those. Okay, and so it's in NP just the same as SAT was. And hopefully it's pretty clear that it would probably the known NP complete problem that we want to reduce to 3 CNF Sat is satisfiability. So this Sat can have any number of literals, okay, in its clauses. It doesn't have to just have 3. So we're going to take any arbitrary number and convert it into an equivalent problem where every clause has only 3. Okay. So let's look at the reduction of how we do that. So the reduction algorithm has 3 steps. So the first phase, or the first step of the reduction, the polynomial time reduction, is to kind of construct a binary parse tree, okay, for the input formula. So all of the leaves of this tree will be the literals, and then all the connectives, all of the logic functions will be our internal notes. Okay. So if we look at how we do this, we have this formula. Okay. This formula is a SAT formula, so we're taking a general SAT formula. It can have any number of literals in its clauses or its different cases, all right, and we have to turn it into 3 CNF. Okay, this one doesn't even have to be in conjunctive normal form, so it's just any formula. All right, so if we look at this, all right, in terms of precedence, the things that will happen is there's this expression in parentheses, and that's going to get anded with the result of this NOT gate. Okay. So notice over in our parse tree, okay, there's an AND gate, okay, and there's 2 things that are ANDed together. There's something on the left that's happening down in this tree, and in the right there's the negation of x2. Okay, so that is the literal, that's a leaf. Okay, we've come to an actual literal, and so that's at a leaf. Okay, but on the left side of the tree, we have a more complicated expression, and so we have to look at, all right, well, where is this parenthesized? Like, where's the precedence happening? Well, this is really an or of 2 things. This expression on the left, and then the negation of this thing on the right. Okay, so we've got an OR of two things. We've got an OR of something on the left, that's this expression, and the negation of something on the right. So let's go to the left. Well, the left is an implication, so there's an implication here of x1 implies x2. So we've gotten down to our leaves here, and then we go back to the OR. Okay, the thing on the right, the second argument of the OR is a negation of something. Okay, so notice there's a negation of what? Well, this expression corresponds to this, this branch of the tree corresponds to this expression. That expression is an OR of two things, this expression and x4. So we have an OR of an expression in x4. We can stop at the right branch of that tree because we've gotten to a literal, but the left branch, okay, well, the left branch, when we look at this expression, that is a biconditional of two literals, not x1 and x3. So we have a biconditional of not x1 and x3. Okay. All right, so this tree just represents, how this expression works. So once we have that expression, we can go and we can just label all of the internal nodes with a new variable, y1, y2, y3, y4, y5, y6. Okay, so we just label, essentially it's the output of these internal nodes. Okay, and then very similar to what we did in our previous example, we are going to create a formula that ANDs together the final output, which should be at the top, okay, and then for each internal node, we're going to look at the output and have it be a biconditional with the logical functionality of whatever that node is doing. Okay, so y1, the output of this node, is logically equivalent to the AND of the left side, which is y2, and the right side, which is the negation of x2. If I look at y2, that's over here, the output of that is logically equivalent to the OR of its left side, which is y3, and its right side, which is y4. If I go to y3, it's logically equivalent to the implication of the left side implies the right side. If I go to y4, that's logically equivalent to the negation of y5. If I go to y5, that's logically equivalent to the left side y6 ORed with the right side x4. y6 is logically equivalent to the negation of x1 and with the biconditional with x3. Okay. So again, this is expressing that the output is 1, and then these are all expressing that the different operators do the function that they're expected to do. Okay. All right, so this is the first step. That's step 1. So once we have a formula in this form, so notice it's still not 3 Cnf Sat. Okay, so it's not in conjunctive normal form because it's not a conjunction of disjunctions. Okay, and we also don't have 3 literals in every individual thing that's ANDed together. So we still have a lot of work to do to get this into an instance of 3 Cnf Sat. So the next step, step 2, is going to convert the expression into conjunctive normal form. So to do that, we're going to look at each individual expression that gets ANDed together, and we're going to make a truth table for that expression, and then write that particular expression in disjunctive normal form for the negation of the value of that expression. Okay, And then we're going to negate that to get the actual expression that we want. And when we negate that, we'll use De Morgan's law, and it'll go from disjunctive form, normal form, into conjunctive normal form. So let's look at how that works. Okay, so for instance, we have this expression right here, y1, if and only if, y2, and not x2. Okay, so this one has 1, 2, 3 different variables in it. So if I were to make a truth table, I would list my 3 variables, y1, y2, and x2. Okay, if there's 3 variables, there's 8 different possible truth assignments to those variables. So I fill out my truth table, and then I look at the output for each of my 8 possible inputs. So, for example, if I have, all true, 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 like y2 would be true, and then not x2 would be false, true and false would be false, and then when I have y1, which is true, true, if and only if false, that evaluates to false. That's where the 0 came from. And I would go through each line and do that. Okay, the second line here, y2, that's true, not x2, that's true, true and true is true. And then I would have y1 true, if and only if true, yes, that one evaluates to true. Okay. So I do the same, so I just do that for every single possible assignment of values. So once I have my truth table figured out, then I want to write a disjunctive normal form for not the phi sub I. Okay, so I'm going to go through and look for all the places where this is 0. Okay, because we're looking for not the negation of the formula being true. Okay, so I'm going to look for where it's 0, which is here, 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 and here. And I'm going to write the disjunction for this one. So to get this to be, this will be 0. Okay, so when I have y1 is true and y2 is true and x2 is true. So if I come down here, the negation of phi sub 1, this is phi sub 1. Okay, this first 0 is y1, y2, and x2. That shows up here. Okay, so that's one way that we could get 0. Another way is here. So that would be y1 is true, y2 is false. We'd have to put not y2, and x2 is true. So and x2. Okay. So this y1, not y2, x2 corresponds to this 0. Okay. Or another way is this 0. So I move over to here. That would be where y2 is true, so y1. And then y2 and x2 are both false. So we'd have y1 and not y2 and not x2. And then there's one more 0 to take care of down here. Okay, and that one will be not y1 and y2 and not x2. Okay. So that expression will give me the negation for just that first one. I mean, I would have to do that for all of these. Okay, I'm just doing it for the first one right now. Okay. Of course, my formula really wants not where this is 0, but where this is 1. So I negate this, and when I negate this one, that means I would have to negate this whole, so if I negate this, then I would have to negate this whole thing. And then I use De Morgan's law to negate that. And so De Morgan's law says when I negate something, that I will negate each individual clause in here, and all of these ors turn into ands. So notice this or turns into an and, this or turns into an and, this or turns into an and then I would negate each individual one. So when I negate that, okay, all of the ands turns into ors, so that and turns into an or, that and turns into an or, and I negate each individual literal in there as well. So y1 becomes not y1, y2 becomes not y2, x2 becomes not x2. Okay. So essentially, all of the ands become ors, all of the ors become ands, and we negate each individual literal. Okay, and so that's what we do. So notice all of those literals are negated, all of the ands are turned into ors. So now this right here is in conjunctive normal form because I have a conjunction here of disjunctions. These are all disjunctions. Okay, so this is in conjunctive normal form. So I would have to go through and do that for every single one of these. Okay, so the other one that I did for you right here is the Y4 if and only if not Y5. Okay, because that has a fewer number of variables, so that's an interesting one to look at. Okay, so this one only has 2 variables, and so we're only going to have 4 rows in our truth table. And then we go through and we just evaluate the expression Y4 if and only if not Y5. Okay, so not Y5 would be 0, 1, if and only if 0 is 0. Here, Y5 is 0, so not Y5 is 1. We have 1, if and only if 1, that gives us 1. Okay. Here, not Y5 is 0. 0, if and only if 0 is also 1. And then the last, okay, when not Y5 is 1, we'd have 0, if and only if 1, that gives us 0. Okay, so we just fill out the truth table, and then we do the same thing we did before. So we look for all the zeros, okay, there's 2 of them, and then we write the expression for where this one is 0. So that's when Y4 and Y5 are both true. So Y4 and Y5. Okay, and then the other zeros down here, that's when they're both false. So that would be not Y4 and not Y5. Okay, of course, now we looked for zeros, so that's where this one was false. But what we're really interested in is where it's true. So we have to negate this side, and when we negate this side, we negate this whole side. Okay, when we negate it and apply De Morgan's laws, all of the literals, so the Y4 becomes not Y4, Y5 becomes not Y5, we just negate all of the literals, and all of the ands turns to ors. All of the or turns to and, the and turns to or. Okay. And so now this is in conjunctive normal form because we have a conjunction of these 2 disjunctions. Okay, so that completes step 2. Okay, so one thing that we'll notice is that this has 3 distinct literals, this has 3 distinct literals, this has 3, this has 3. That's great. This, you know, if we were looking at this one, that's in 3 CNF. But this one only has 2 literals in each of these clauses. So this one doesn't have 3 literals. So we're almost there, but we still need to have exactly 3 literals in every clause. And so the final step of the algorithm is to ensure that every clause has exactly 3 distinct literals. So we're going to go through all of the expressions that we generated, and if we already have 3 literals, then that's great. We just keep them as they are. But if we have a clause that only has 2 distinct literals, okay, so literal 1 or literal 2, it looks like that, then we would replace that clause with 2 different ones, L1 or L2 or P, and L1 or L2 or not P. Now this is logically equivalent to the original one. So if I think about this in terms of logic, okay, I'm going to do this on the side. So I have like literal 1 or literal 2 or P, and that's ANDed with literal 1 or literal 2 or not P. Okay. And so if I kind of think of these ors, or is associative, so I can kind of group this together and group this together. And then I have this common L1 or L2. So according to the distributive law, I can take L1 or L2 out. Okay. And then I can AND that. Or that with P, so that would be L1 or L2 or P, so L1 or L2 or P, and then over here I would have to do not P. Okay, so doing the distributive law, I would have L1 or L2 or P, that gives us this one, and L1 or L2 or not P, that gives us this one. Okay, well, P and not P, that always evaluates to false. This is a contradiction. Okay, and anything ORed with false, it will depend on the value of L1 or L2. That is an identity for OR. Okay, so what basically we're just saying is I'm going to, if I only have two literals like this, I can kind of work this backwards and replace it with these two clauses that are logically equivalent, but they have three different literals. Okay. So, and then in a similar way, if you went through the logic on this one, if I had only one distinct literal, then I would have to replace it with these four clauses that are logically equivalent to something that just contains one. Okay, so imagine here where I have these two distinct literals. This one would become not Y4 or not Y5 or P, and not Y4 or not Y5 or not P. And then this one, I would have to do that as well, so I'd have ANDed with, and then I would have Y4 or Y5 or P, and Y4 or Y5 or not P. Okay, and so now I've turned this from having only two distinct literals in each clause to having three distinct literals in each clause. Okay, and now since my final formula that I have is in 3 Cnf form, and it's logically equivalent to the original one, it's only satisfiable if and only if the original one is satisfiable. Okay. Also, it's polynomial in the length of the original formula. Okay, where you're going to replace each formula with at most, 4. So we might have one expression here, and it might turn into at most four expressions. 2 with two literals. If we had only one literal, it would turn into 4. But a maximum of 4 clauses per one. Okay, and so it will be polynomial in the length of the original formula. Okay, and everything is accomplished in polynomial time. So that is the reduction of general satisfiability to 3 Cnf satisfiability, and so 3 Sat is also NP complete.